Hello, am I audible? Hello, Andiraj V. Okay, okay. So my screen is also visible, right? Okay, so I will start from around 7:15 after everyone comes, and then I will go to the things that we are going to discuss. Okay. So do you have any doubt from the previous class itself? Okay, but uh, okay. The assignments that is given by the professor, we can discuss it later on. You were unable to attend the last class, so the YouTube link I have shared in the chat itself. So you can go to the lecture and yeah, it is recording is available on my YouTube channel. So I have already shared the link, so you can go through it. I'm sharing it again. So yeah, yeah, I am doing it. Let me just- So, oh, hmm. So, so can you access now? Can you see in the chat box? I've shared the previous meeting link, the recording itself. So you can go to the video and can check it that whether it is working or not. I hope it is working. And the assignment which is given by the professor that you can mail me and then I will look into it, or otherwise I can also download and look into it and then we'll come back to you. And the doubts you have, you can mail me. I think that will be better. My email ID I am sharing, so you can mail me your doubts and the assignment itself, so that I will then discuss it in the next week. Okay. So let other people join the meeting. I think from 7:15 I will start. Okay. Hello, am I audible? I think we should start. Other others will join one by one. So today I'm going to discuss about some of the basic principles of fluid mechanics, and I think which will be very much common to the fluid mechanics course you had during your bachelor's. So this is a bit kind of introduction, and then we will be going towards the computational aspect of it. So today I'm going to discuss about the different type of coordinate systems, vector, tensors, Kronecker delta, Levi-Civita symbol or unit alternating tensor, different operations of tensors and vectors, curl, gradient, vorticity, and also different kind of what should I say, the Lagrangian and the Eulerian approach. This kind of things I will go through today. So it's a bit of a kind of recapitulation of what you have studied during your bachelor's. So I think we should start. So as you all know that there are three kind of coordinate system. One is basically called the Cartesian coordinate system. Uh, Cartesian coordinate system, and another one is basically called the cylindrical coordinate system, and the third one being the spherical coordinate system. Okay, so going to the Cartesian coordinate system, as we all know, this is one, this is two, this is three, and this is one. So there is a point P on the XYZ plane, and this point P is basically having a coordinate X, Y, and Z, and O is origin, and this one is basically the z-axis, this one is a x-axis, and this one is a y-axis. Start in Canada. So going to that of the this point itself, which is p is basically a function of x, y, and z. So OP vector, which is a vector which is pointing from the origin to the p point itself. So OP vector is basically equal to OR vector I cap plus OS vector j cap plus uh, another one is basically let us consider to be this is OR, this is OS, and this is OT, OT vector theta. Okay, so which is basically X I cap plus Y j cap plus Z theta. Okay, then defining the variable R, where R is basically x square plus y square plus z square. So OP vector is basically equal to R L I cap plus M j cap plus M theta, where L is basically equal to what? X by root over of x square plus y square plus z square. M is basically what? Y by root over x square plus y square plus z square, and M is z by root over x square plus y square plus z square. So these are basically the cosine of the angle this OP vector is making with that of the x-axis, y-axis, and the z-axis. Okay, so is it clear to all of you? This part, this is cos alpha, this is cos beta, and this is cos term. Okay, so going to the next part itself. So do all of you know the what should I say? Let's not go to that part. I think I should carry forward with the cylindrical coordinate system. So this one is basically called the cylindrical coordinate system. So this is a z-axis, and this is basically the r vector, or the er cap vector, you can call it to be the unit vector along the radial direction. And then this is actually moving along the theta direction. So this is basically the erase this one is theta. So this one is basically e theta cap. Okay, and there is a point P similar to that, which is present in that of the cylindrical coordinate system itself. So which is a function of r theta and z. Okay, so all of us know that x equal to r cos theta, because this radius vector is here. The theta is basically the angle the radius vector. I actually clean this one out. Clean it a bit. So this one is basically the x-axis, this is the y-axis, and this is the z-axis. This is r vector, and this one is a theta. So this is er cap, and this is e theta cap. Okay. So now x equal to r cos theta, because x is basically the cosine component of the this radius vector itself, and y equal to r sine theta, and z equal to z. Okay. So OP can be written as, if I want to write it in er e theta and ez cap, that can be written as r er cap plus r theta e theta cap plus z ez cap. So r theta, because k is equal to r theta. So this is basically in the theta direction, the distance we are traveling. So in the radial direction, we are having the r radius vector in the radial direction. So OP vector in the cylindrical coordinate system, which is basically this one out, but P is a point which is a function of r theta and z. So we can write it as r er cap plus r theta e theta cap plus z ez cap, where er cap, e theta cap, and ez cap, they are basically the unit vectors along r theta and z direction. Is it clear to all of you? Okay. So then going to that of the spherical coordinate system. Uh, so this one is a z. This is sound. Yeah. So this one is a z, and this one is a y, and this one is a x. So now I have to draw a sphere. So this one is a spherical coordinate system. So now this radius vector is basically, this one is r is a radius vector and theta is the angle made by the radius vector with the z-axis. And similarly, if I take the projection of the radius vector on the xy plane, which is basically r sine theta, since this angle is basically 90 minus theta, and the angle this r sine theta actually makes with that of the x-axis, this is denoted by another angle phi. Okay, so if this one is basically a sphere and P is a point on the surface of the sphere where it is a function of r theta and phi, then this is basically the radius vector. So then we know the relation between that of the Cartesian system and the spherical coordinate system. So this is basically ER cap along the radius vector direction. So if I want to rotate it in this direction, E theta cap it is. And now when I'm rotating in this direction itself, it is E theta cap. And then if I'm rotating in the XY plane itself, so this becomes E phi cap. So the direction of the this angular coordinate system, this angles itself, this E theta cap and E phi cap is basically the direction in which the phi and the theta angle are increasing. Okay. And this ER cap is basically in the direction of the radius vector. Are you able to understand this? Do you have any doubts? Rushikesh, Anand, Panditaraj. Uh, can you be please be louder? I am unable to hear you. So ER is basically the unit vector along the radial direction. So you have a radius on the sphere itself, which is basically coming from the, which is extending from the center to that of the outer circumference of the sphere. So if I want to, this is not your conventional XYZ vector. Okay. So it has three vectors, which is ER cap, E theta cap, and E phi cap. So these are basically the unit vectors. Okay. So ER cap is basically in the direction of the radius vector. Okay. So E theta cap is basically in the direction where the theta angle changes. Okay. This is basically called the E theta cap. Okay. And then uh, if it is actually moving in a direction in which this phi increases, which is on the xy plane, your radial vector actually increases, then it is called E phi cap. Okay. So is it clear, Rushikesh? Okay. So these are basically called the curvilinear coordinate system. So this is basically giving you the direction in which the r, theta, and the phi increases or decreases. So if I want to find out the relation between that of the Cartesian coordinate system and a spherical coordinate system, so x is basically what? R sine theta cos phi. Why this thing? Because this radius vector is making the theta angle with that of the z axis. Then on the xy plane, it is making an angle what? 90 minus theta. So on the xy plane, this radius vector will be what? R sine theta. Okay. Then I have to take the component of r sine theta on the x-axis. So it becomes r sine theta cos phi. Is it clear to all of you? Anand, Rushikesh. Okay. So now y is basically equal to what? R sine theta sine phi. Similarly, if I go to z, it becomes uh, cos theta, r cos theta. Sorry. And then if I want to write it in the format of OP vector, then it becomes E r cap plus r theta E theta cap plus r phi sine theta E phi cap. Why r E r cap? Because r is basically the length of the radius in the E r cap direction. Why r theta E theta cap? Because A is equal to r theta we know. So your the length which is basically subtended by the this E theta cap direction on the circumference itself. So this is basically A is equal to r theta. So r is a radius and theta is the angle which is uh, the theta is the angle which is traveled by that of the point P itself. So that's why it is r theta. And then when I am actually increasing this E phi cap, so E phi cap actually lies on the xy plane. So what I have to do, I have to take the component of sine theta, the component of r, which becomes r sine theta. So r sine theta multiplied by phi, which actually gives you this r phi sine theta. So we are also using here this a is equal to r theta component, the concept, but here your r actually becomes r sine theta, since you are actually projecting this radial vector on the xy plane. Okay, so this is r phi sine theta e phi cap. So if I want to express in terms of this ER cap, E theta cap, and E phi cap, so it will be like this. And now if I want to express in terms of xy coordinate system, that is Cartesian coordinate system, so it will be your I cap or ex cap plus r sin theta cos phi sin phi ey cap plus r sin theta r cos theta, sorry, r cos theta ez cap. Okay. So ex cap is basically your I cap, and ey is basically your j cap, and ez is basically your k cap. So you can express in terms of ex, ey, and ez, or you can express in terms of r theta phi. It is up to you what you do. Okay. So is it clear to all of you? Hello, am I audible? So can you please be a bit louder? Do you have any doubt regarding the concepts that are shown here in the screen? Rushikesh, can you please be a bit louder? It is clear. Okay. So it is clear, right? Okay. So I have no issue you being asking any kind of doubts. So you ask any kind of doubt, otherwise we can go ahead so that we can cover many things that we want to discuss in the class itself. Otherwise, it actually I have to ask you multiple times, which actually uh, reduces our time. So now A vector is basically, if I take similar to that of the, if I go back to the Cartesian coordinate system, then this P point or A point itself, whatever you call it to be. So this is X, this is Y, and this is Z. So this A vector is basically can be written as A1 U1 cap plus A2 E2 cap plus A3 E3 cap. So initially I actually introduced you to three coordinate system, the Cartesian coordinate system, the cylindrical coordinate system, and the spherical coordinate system. But in our uh, class onwards, we will be discussing only the Cartesian coordinate system. Any kind of derivations we are going to make, that we are going to make by using the Cartesian coordinate system. So now your E1 cap is basically same as EX cap or I cap, or this one is same as EY cap or J cap, whatever you call it to be, or this is written as EZ cap, K cap. So multiple different kind of notations are basically used in different books, but they basically mean the same. So A1 is basically the length along the x-axis, A2 is the length along the y-axis, and A3 is the length along the z-axis. Okay, so that's how you reach the point. So you go A1 along the x-axis, then you go A2 along the y-axis, and then you kind of go to the point A itself by going A3 along the z-axis. So that's why it is A1 U1 cap plus A2 E2 cap plus A3 E3. Then going to that of the vector itself. So vectors are quantities which has one direction and one magnitude. Okay. So is it clear to all of you? What do you mean by vector? Okay. So this A vector, if I want to add with a B vector itself, so this will be equal to that of AI EI cap plus BJ EJ cap. Okay. So as I'm using a reduced notation, which is AI EI cap, so this is basically equal to A1 E1 cap plus A2 E2 cap plus sorry, A2 E2 cap plus A3 E3 cap. Okay. So there is an invisible summation there. So typically it means that we will see in books also. This actually means I equal to 1 to 3 AI, EI cap. Okay. Similarly, if I'm actually using this J coefficient, so this is basically equal to J equals to 1 to 3, AJ, BJ cap. Sorry, BJ, BJ cap. Okay. So if I add these two quantities, so this will be equal to sigma I equal to 1 to 3, AI, EI cap, and this will be sigma J equals to 1 to 3, BJ, BJ. Okay. So this will be equal to A1, E1 cap plus A2, E2 cap plus A3, E3 cap plus B1, E1 cap plus B2, E2 cap plus B3, E3 cap. Okay. So this will be equal to A1 plus B1, E1 cap, A2 plus B2, E2 cap, A3 plus B3, E3. Okay. So is it clear to all of you? Okay. So now, if I actually write it in a index notation, so it will be like AI plus BI, BI cap. Okay. So those components will be basically added where I equals to j. So the coefficient of x will be added with x, the coefficient of y unit vector will be added with the y unit vector, and the coefficient of z unit vector will be added with the z unit vector. That's how it works. Okay. So if I go to the physical interpretation of it, so so if this one is basically, or I can go to the previous page also. So this one is a vector, is an a vector, and this one is a b vector. So a plus b is basically the addition of the two vectors, okay, or the resultant vector itself. And similarly, we can also define a minus b vector. So it becomes ai ei cap minus of bj ej cap, and which will be equal to ai minus bi bi cap. Okay. So now if this one is b vector and this one is a vector, so now this one actually becomes minus of b vector, and the resultant vector is what? A vector minus b vector, or the diagonal of the parallelogram which is created by that of the a vector and the b vector. Okay, so that's how it works. A plus b and a minus b. These physical interpretations are pretty much useful, or it will help you regarding further analysis of fluid mechanics problem. So there is another operation which is called multiplication. So multiplication is basically if I want to multiply a vector by a scalar, where alpha is a scalar. So this alpha ai ei cap, and this one is basically ai prime ei cap. Okay. So ai prime is basically what? Alpha ei. So if your a vector is basically like this, so alpha times ai will be what? If alpha is greater than 1, it will be longer. If alpha is less than 1, that will be shorter. Okay. So is it clear to all of you? Hello, Rushikesh, Anand, Anirudh, Pandiyaraj. It is clear, right? So, okay. So there is another concept which is called the scalar or the dot product. Okay, dot product. So how does it function? So A dot B, which is called the scalar product between A vector and B vector. Okay. So A dot B is equal to magnitude of A, magnitude of B cos theta. And this this is also represented as A dot B as AI EI cap dot BJ EJ cap, which is basically AI BJ EI dot EJ cap and AI BJ delta IJ. So this is basically called the Kronecker delta. Okay. So delta IJ is basically equal to 0 if I not equal to j, and it is equal to 1 if I equal to j. And we know that if I actually do the scalar product between the two vectors, so it will be like a1 b1 plus a2 b2 plus a3 b3. So what we are doing is basically, sorry, b3. So what we are doing is basically we are basically multiplying the scalar components of the vector in the x direction, y direction, and the z direction respectively. Since we know that ex cap dot ex cap or I cap dot I cap, whatever you call it to be, this is equal to 1. Since this is basically what? I cap magnitude, I cap magnitude, and cos of 0. So cos of 0 is 1, and I cap magnitude is 1. So that's why it actually remains. So when you multiply a vector with another non-orthogonal component, then you basically are not get a non-zero scalar product. But if you are actually multiplying two orthogonal components, like orthogonal vectors, like I cap dot j cap, which are orthogonal to each other, then it becomes what? Magnitude of I, magnitude of j, and then this j cap, and then cos of 90, which actually becomes 0. Okay. Or even if I do with I cap with k cap, the dot product between the two, it will be 0, since they are orthogonal in nature. Okay. So this is called the scalar or the dot product itself. Scalar because the result we are basically getting by multiplying two vectors is basically a scalar. Okay. So it has no directional dependence. So it has one single value. So is it clear to all of you? Okay. So what if, okay, so what is the interpretation of the scalar product? So if A is basically your vector here, and this is B vector, and theta is the angle between the two. So if I want to take the projection of the B vector on the A vector, for example, this one, so this actually becomes B vector magnitude cos theta. If I'm talking only about the length of the vector, okay. So we all know that A vector dot B vector is equal to A vector magnitude B vector magnitude cos theta. So if I want to get this value B vector magnitude cos theta, so this is A vector dot B vector magnitude of A vector. This is basically the projection of the B vector on the A vector. Projection of B vector on A vector. Similarly, you can also find out the projection of the A vector on the B vector. So what you have to do is basically you have to draw a perpendicular like this, and this becomes actually the projection of the A vector on the B vector, where this becomes A vector magnitude cos theta, this portion itself. Okay, so then this part is basically what? A vector dot B vector by magnitude of B vector. So this is what? Projection of, if, sorry, projection of A vector on B vector. Okay, so is it clear to all of you? Okay, so there is another operation or another thing which is called the index shifting operation. So this is pretty much, for example, you have a vector which is ei cap, ei cap. So you can also write it like ej cap, aj cap, ej cap, delta ij. So I equal to j will basically give you the value of delta ij to be 1, and this actually make it reduce to be like this one. Okay, so you can also change the indices, and then you can also multiply with a Kronecker delta. So these are typically handy when you are going to prove different kind of vector identities. So it actually becomes this kind of things, phase shifting operation or index shifting operation actually becomes handy there. It becomes useful there. So I will give you example regarding this in this course itself. So there is another interpretation of the dot product also, as we know from the physics class that W is basically equal to F dot R, where R is the displacement and F is a force. So dot product actually gives you the work done by an object which is experiencing a force F and which is going through a displacement R. So that is basically called the work done. So that we find out by using a dot product. There is another thing which is called the cross product or vector product. So if you have any doubts, you can interrupt me in the middle and then we can discuss. So what is called a cross product? So A cross B. So in literature, in the book itself, you actually use this as cross product. This one, this cross symbol, but I use this one. Okay, so you can use as you like, but I use this one as a symbol for the cross product. So this one is basically I cap, J cap, and K cap, and this is AX, this is AY, and this is AZ, and BX, BY, and BZ. So this is by using finding the determinant of it, you can find the cross product between A and B. So when you actually make a cross product between A and B, it actually gives you a vector which is perpendicular to both of them, or gives a vector which is in the direction of that of the vector which is perpendicular to both of them. So this one is the angle between them. So A cross B is basically magnitude of A, magnitude of B, sine theta, n cap. So n cap is basically perpendicular to both A and B. So n cap is this direction. And here I can use this A vector as this one, or there is an underline, this curled underline I can provide. So both of them actually mean the same. So I may interchangeably use this during our course. So they actually mean the same. So if I make the cross product between the two, so this is basically magnitude of A multiplied by magnitude of B multiplied by sine of the angle, which is the angle between the A vector and the B vector. And this is basically in the direction which is perpendicular to both A and B, which is basically the in cap direction. Okay. So is it clear to all of you? Okay. So are you familiar with these concepts or these are very much new to you? Anyone in the class? Familiar in EG. Okay. So I'm going through this as a kind of a bridge between the conventional fluid dynamics and the computational fluid dynamics. So we are going to use these concepts in future. So it's a kind of recapitulation. So then E I cap and this E J cap, the cross between the two is basically I J K, epsilon I J K E K cap, where epsilon I J K is basically unit alternating tensor, or this is also called the Levi-Civita symbol. Okay, so if I actually make it to be like this, means A cross B. So this is basically A magnitude. Uh, I can write it in the index symbol. So this sign convention I can use epsilon I j k e k cap. So epsilon I j k is basically equal to 1 if it is I, j and k, if it is actually moving in this direction. So if it is epsilon I j k is equal to j k I equal to kij, this is basically equal to 1. But if I change the direction of the rotation, so if I actually make it to be anti-clockwise, then this ikj or kji or jik, this will be minus 1. And if two of the indices actually become same, for example, it is becoming iij, so or epsilon kkj, this thing will be equal to 0. If two of the indices actually become same. Okay. So if I actually break this system, so aibj epsilon ijk, this is ek cap because we know that ek cap is perpendicular to both ei cap and ej cap. The vector we are getting is basically perpendicular to both a vector and b vector, and I is basically varying from 1 to 3. J is basically varying from 1 to 3. Bj epsilon ijk ek cap. Okay. So these are basically we are done it right. Okay. Okay. So this will also vary from 1 to 3. So what the three indices is, this is I, J, and K itself. We are basically having this sigma symbol over which we are kind of uh, what should I say? We are kind of going to do the summation. So we are going to get some 27 components, and these 27 components, out of which if I simplify, this actually becomes this E I cap or E1 cap, E2 cap, and E3 cap, and this is because this is becomes A1, E2, and E3, and this becomes B1, B2, and B3. Okay. So do you have any doubts until now? Do you have any doubts? Okay. Then going to that of the physical interpretation. Interpretation of cross product. So this cross product actually gives you one physical thing, or which you are very much familiar with, which is basically the moment of a force. The moment of a force in about a point O can be described, where M vector is basically what? R cross F. Okay. as shown in the figure. So this is basically this is a d distance, where this is a o vector, o origin, and this is a direction, this is a radial vector, and theta is the angle between that of the a vector and the r vector. So the moment you are getting is basically r cross f, which is basically magnitude of a r, magnitude of a sin theta n cap. So n cap you determine by right hand or screw rule, which is basically positive if the rotation is happening in the anti-clockwise direction. So if it is actually happening, which is r cross a vector, so this r vector cross a vector, it is happening in the anti-clockwise direction, and that's why it is positive. So if it is happening in the clockwise direction, then it is negative. Okay. So this now this r sin theta, if theta is this angle, r sin theta is d. So this is basically the in vector is basically if d in cap, or you can write it to be like if d. So force multiplied by perpendicular distance. Okay. So is it clear to all of you? Rushikesh, Pandya Anirudh, Utkarsh. So then going to that of the another kind of product, which is called the box product. So box product is basically A cross B dot C. That is basically called the box product. So what is the physical interpretation of box product that we are going to discuss later on. So first see how it looks like. So magnitude of A cross B, C, and this is a cos phi. The angle between the sorry, the angle between the vector which is perpendicular to both A and B and the C vector. So if I write a parallelogram, if I draw a parallelogram like this, so now it is like this thing, this thing, this thing, and this thing, a bit distorted one. So if this one is a B vector and this one is a A vector and this is a C vector, and phi is basically the angle. So if I actually find the direction of the A cross B vector, that is basically same in the direction of C itself. So A cross B dot C vector. So this will basically give you the volume of the parallelepiped. Since A cross B is basically giving you the area of the base itself, the parallelogram, this parallelepiped, sorry. And then what you are doing is basically you are multiplying by the height itself. That is a C vector. So C vector is basically your height vector along this direction. So this is a C vector itself. Okay. So and this one is the angle phi itself, and this is basically A cross B. which is perpendicular to both A and B vector. So what you are doing is basically by A cross E, you are finding out the area of the base itself, this region, and then you are getting this height itself. And then what you are doing is basically the area of the parallelogram. After getting it, you are taking the component along the C vector itself, which is basically giving you the height of the parallelopipe. And this height of the parallelopipe multiplied by that of the this base area, this is basically giving you the volume of the parallelopipe by using this scalar triple product. So this is basically called the box product or scalar triple product. So is it clear to all of you? Okay. So there are some multiple. Okay. So there are some multiple relation between the Kronecker delta and also the this unit alternating tensor of the Levi-Civita symbol. So as of now, I am writing the relation. So if you want the derivation of it, I can send you. But in the class itself, I am not discussing it. So this epsilon ijk and epsilon ijh is basically equal to delta kh, relation between delta and epsilon. Delta ij and epsilon ijk. Then epsilon ijk, epsilon in k is basically delta in delta jn minus delta in delta jn, and epsilon ijk epsilon jki is basically equal to epsilon kij. So if the order is basically in the ijk format, which is after I it is coming to be j, and after j I am getting k, so it is going to be 1. And if I actually change the order, so this is going to be 1. If I change the order, it becomes -1. And if the two of the indices are basically same, if it is like IIK, so then this actually becomes 0. Okay. So this is a relation between these are the different kind of relations between the unit alternating tensor and the Levi-Civita, this Kronecker delta and the unit alternating tensor. This is called the unit alternating tensor. And this one is a Kronecker. So these are the different kind of relations which you are going to use when you are going to prove vector identity. So today I'm going to show you one of the example of how to express a vector triple product in terms of scalar triple product. So that thing I'm going to prove to you. So another physical significance of this is basically if the three vectors are coplanar, vectors are coplanar, which basically means that they are on the same plane, either they are on the xy plane or yz plane or zx plane or any other different plane itself. So then A cross B dot C equal to 0. Okay. Since for example A cross B are basically coplanar, so it will basically give you a vector which is some D vector, and C is also in the same plane as A and B. So what will happen that D vector and C vector will have 90-degree between them. So if I get a dot product between the two vectors which are basically 90-degree, then that will give me a 0 result. So that's how you can prove that why the scalar triple product is basically equal to 0 when three vectors are basically coplanar to each other. And similarly, this A cross C, sorry, uh, B cross C dot A, this is also equal to 0, or C cross A dot b equal to 0. Okay, so that's how it works. So uh, there is one numerical I am giving you, so I hope you can solve it. So there are 3 points. Or oh, please examine whether minus 6 I cap plus 3 j cap plus 2 k cap and 3 I cap minus 2 j cap plus 4 k cap and 5 I cap plus 7 j cap plus 3 k cap and minus 13 I cap plus 17 j cap minus k cap are coplanar or not. Those are these 4 points. Okay. So can you please numerically investigate this thing, that whether they are coplanar or not? Okay. So is it clear to all of you? Hello, am I audible? Rushikesh, Anirudh, Utkarsh. Okay. So what you have to do is basically you have to find this. This is basically your OE vector or OB vector or OC vector and OD vector. Okay. So what you have to do is basically you have to find that whether they are coplanar or not. So you find the square triple product between them. That is a box product between them. So this is A vector, B vector, and C vector. If I want to find out the box product, this is basically A1, A2, A3, B1, B2, B3, and C1, C2, C3. This is basically equal to 0. Okay. This thing you have to prove. Okay. So this you can reduce like this is your AB vector, and this one is basically your BC vector, and similar this one is your CD vector. So AB vector is basically like OA vector minus OB vector. Similarly, for the other case, you have to find out, and then you have to find out the AB vector, BC vector, and CD vector. You basically have to find out the scalar triple product between the two, or the box product between these three vectors. And then if that is equal to 0, then your 4 points, which is basically this one, this one, this one, and this one, they are basically coplanar. Okay. So is it clear to all of you? Okay. So I am giving you 10 minutes. So you solve it and then we go ahead. Okay. So if you are able to solve it earlier, you can also ping me and then we can go ahead also. I think it's an easy problem. So are you able to figure it out? So whether they are coplanar or not, they are co equal to zero. No? Oh, that should be the answer. So you basically get a matrix like this: 9 minus 5, 2, 11, 4, 1, minus 7, 14, and minus 3. So this is basically becomes zero. So now I'm going to that of the there is another operation which is called the vector triple product. I hope everyone is able to figure it out. So they can do it at home also if you are not able to figure it out. So this is basically called A cross B cross C. This is called the scalar triple product. Okay. Sorry, vector triple product. Yes, I agree with you. So vector triple product. So this one is AI E I cap cross BJ EJ cap cross CK EK cap. Okay. So now what I'm going to do is basically I want to find out the relation between or expand this vector triple product by using the sign convention that I've or the unit convention that I've discussed before. So how to find it out? So these are basically this kind of convention, this CK EK cap we basically use in order to make it much more easy to write. Otherwise, if I write it to be like C1 E1 cap plus C2 E2 cap, so this actually makes it difficult to follow through. So this kind of text reducing conventions are basically becomes very much handy in nature. So I'm going to show you how to deal with it. So this AI, BJ, and CK are basically they are scalars. So they actually come to one side, and then this EI cap cross EJ cap cross EK cap. Okay. Then what I have to do is basically this AI, BJ, CK, and this actually becomes epsilon IJM EM cap cross EK cap. Then this is AI, BJ, CK, epsilon IJM, epsilon MKM, EM cap. Okay. Since I have said you earlier that if you want to, if you're crossing this EI cross EJ, it actually becomes epsilon IJM EM cap. Okay. So now AI, BJ, CK, and this actually becomes EM cap. Then epsilon IJM and epsilon MKN are the two unit alternating tensors which are present here. So we can break them out by putting a minus sign here. So what I have to do is basically uh, mm, MIJ epsilon MKN. Okay, percent. And then what I have to do is basically EI BJ CK EN cap delta IN delta JK minus delta IK delta JN. Okay, so now this can be written as minus of AI BJ CK delta IN delta JK EN cap plus AI BJ CK delta IK delta JN EN cap, and this actually becomes AI BJ. This is CJ since delta JK equals to 1 if J equals to K, and I am also making it to be I equals to N since I want to make it to be 1. So it doesn't matter whether I take it to be I or N. So this EI cap. Similarly, the second expression comes to be EI BJ CI EJ cap. So then we can reduce it like C I A I or some mistake. Okay, okay. No, I'm not making a mistake. So this is becoming this expression actually comes here the first one. So CI BJ BJ cap minus of CJ BJ AI EI cap C dot A dot B minus of C dot B A. Sorry, this should be B. Okay. So now we can basically express this vector triple product, or you can expand this vector triple product in this format. So this one is basically A cross B cross C. Okay. So A cross B cross C is basically equal to C dot AB minus of C dot BA. Okay. So is it clear to all of you? Hello, am I audible? So first what I did was actually I took the vector triple product, and then instead of A itself I write it to be like this AI cap, and similarly in place of B I wrote it to be like AJ BJ cap, and in place of C I'm writing it to be like CK cap. And then what I'm doing is basically I'm forming out the cross product between the this EI and EJ, and then cross product with EK, since these are basically the scalars, they CK, PJ and EI. So this actually goes to the left. Then what I'm doing is basically this cross product is giving me one unit vector which is EM cap, and this unit alternating tensor. Similarly, this EM cap cross EK cap is basically giving me another unit vector which is EM cap. And then what I'm doing is I'm multiplying this epsilon ij with epsilon mk. So this is giving me in terms of I have to express in terms of deltas. So which I have done it here by using the identity that I have described previously in the class. And then what I'm going to do is basically using these identities, I have to replace, after using this identity, I have to replace delta ik and delta j. So delta ik is basically equal to 1 when I equals to k, and jn equals to 1 when j equals to n. So I have to put this out in this equation, and then I have to simplify it in this format. So it actually comes out to be like C dot AP minus of C dot BP. Okay. So is it clear to all of you? Okay. So there is another concept which is now I'm going to the vector calculus, where we actually beside this subtraction, addition and different kind of vector operation, dot product, scalar triple product, vector triple product and cross product, we are going to discuss about the derivatives of the vector. Okay. Because everything actually, any kind of flow or any kind of or should I say any kind of flux actually depends upon the gradient of the quantity. So here we are going to discuss about the vector calculus. So vector calculus. So this gradient is basically this Dale operator, which is called not the gradient, but this one is called the Dale operator, is basically I cap ddx plus j cap ddy plus k cap dtz. Okay. So I think you can be a bit louder, otherwise it becomes difficult to hear. Okay. So this gradient of phi, where phi is a scalar field, this actually becomes I phi I cap d phi dx plus j cap d phi dy plus k cap d phi dz. Okay. where phi is a scalar field. So what is the physical significance of it? What direction this gradient of phi is actually showing? So if this is basically your phi scalar field, so now if I want to find out this gradient of phi, it is basically giving me the direction in this rate of change of this phi is maximum. So gradient of phi, gradient of phi is giving me the direction in which the rate of change of phi is maximum. Okay. So now if I want to find out a unit normal vector, which is basically the direction of the gradient of phi divided by the magnitude of phi, this will basically give you the unit normal vector, which is normal to that of the scalar field phi itself. This is n cap, so n cap is basically gradient of phi divided by magnitude of gradient of phi, and phi is his scalar field. Then, for example, this phi scalar field, if I'm using a mathematical equation like this, x of y cube z square minus 4 equal to 0, then gradient of phi at p. So this basically you have to find it out. So what you will do is basically I cap ddx of phi, uh, sorry, ddx of phi at point p plus y j cap d phi dy at point p plus k cap ddz of phi at point p. So p point is basically minus 1 comma minus 1 comma 2. So you can find it out. So I want to find out the value itself, the value of this gradient. Okay. So then I want you to find out the unit normal vector, which is gradient of phi uh, at point P divided by the magnitude of gradient of phi. Okay. So please do it. Rushikesh, Anirudh. So do you have any doubt regarding the statement, the problem that I've given you to solve? Okay. So you do it. So gradient, I am showing you how to find it. So d phi dx is basically if I want to find out the x component, that is I cap multiplied by d phi dx. So I cap and d phi dx is basically what? Y cube z square, and this is a constant, so that will be 0. Okay. So this will be the x component. And here you have to put the value of y and z. So y equals to minus 1 and z equals to 2. So it becomes minus 1 minus 4 I cap. Okay. The x component. So similarly, you have to find out the value of the y component and z component, and after finding it out you have to normalize it or find out the unit normal vector, so which is basically gradient of phi divided by magnitude of gradient of phi. So I think that is pretty much easy, so please do it. So, are you done with it, Pandira? Yeah, yeah, do it. No issue. So, your turn, Pandira. So, what is let me do it and let me do it and let me do it and see whether it is same as that of the what is it. So, gradient of phi is basically uh, you have to and okay. And this, it is right. And then you have basically taken the magnitude of that thing and then divided by that. Okay. So this will come as minus of 4 I cap plus minus of 12 j cap plus 4 k cap, 4 k cap. Yep. This will come as minus of root over of 11 I cap plus 3 j cap minus k. Okay. Okay. So now if I want you to find out the directional derivative. So there is another terminology which is called the directional derivative. So previously I actually told you to find out the direction of the normal vector or the direction in which you are getting the maximum change. Now I want you to find out the directional derivative. Okay. So this is pretty much similar. For example, there is a surface like phi, where phi is a scalar field as previously told. And then what you have to do is basically you have to take this in cap vector and this in one cap vector. So in one cap is not necessarily your gradient of phi divided by magnitude of gradient of phi. So this is an arbitrary unit vector. So this is not essentially your normal vector. So what you have to do is basically you have to find out the rate of change of phi, that is the gradient of phi along this n1 cap direction. So for example, if your phi is xy square plus yz cube, okay. So what you have to do is basically you have to find the gradient of phi, this gradient of phi itself, and then you have to dot product in the direction of n1 cap. Since I want to find out the rate of change of phi, that is a gradient of phi along in one cap direction. Okay, so do you able to understand it, Pandira? So typically I'm giving you some in one cap and I want to find out the rate of change of phi along this in one cap direction. Okay, okay. So this is a problem itself. So x square plus yz cube. So what you have to do is basically you have to find out the gradient of phi at point P itself. So now your P is 2 minus 1 and 1, and this one is basically your n1 cap is I cap plus 2j cap plus 2k cap. So I think you can pretty much easily find it out. Yeah, I think you can require some 5 minutes to do it. So you do it and then you ping. Okay? Yeah. Mm, 1 second. Means can you please repeat what you said? So 1 second. So this gradient of phi you have to find out and dot of in1 cap. So in1 cap is basically given here and gradient of phi you have to find out at point P. Okay. So I want to find you to find it out the directional derivative of phi, which is gradient of phi at point P along direction in one cap. Okay. Okay. Or you can also frame it at directional derivative of phi along in one cap at point P. That you have to find out, which is basically gradient of phi at point P dot in one cap. Rushikesh, am I audible to you? So you are able to understand what I am teaching, right? Okay. So did you get the answer? With respect to B direction, it is zero. I think you made some error. Let me do it. So gradient of phi will find out to be at point P is basically y squared I cap plus 2xy plus z cube j cap plus 3y z squared k cap, and this is at point P. So if I put the value of 2 minus 1 and 1, it will come to be as I cap minus 3 j cap plus 2 k cap. And then if I want to find out the directional derivative, which I am writing here as dv, so directional derivative at point P along the given direction, so that is equal to I cap minus 3j cap plus 2k cap dot I cap plus 2k cap plus 2k cap divided by root over of 9. So this will come as 1 minus 6 plus 4 divided by 3, and this will come as some as 4. Hmm. So minus 1 by 3 it is coming. Uh, so what I'm doing is basically find out the gradient of phi itself. So gradient of phi is coming to be this hmm, or x square plus yz square. This is basically equal to phi. So this is gradient of phi along x direction. So if I take the derivative with respect to x, it comes to be y squared I cap plus of 2xy plus z cube. It comes when I take the derivative of xy squared plus yz squared with respect to that of y. So if I take the derivative of this thing with respect to that of y, it comes to be 2xy plus z squared. Okay, and this one coming to be okay. This should be z cube. Sorry. So this should be z cube. I have given it to be z cube. Yeah. So this should be z cube. So if I take the derivative with respect to y, it comes to be z cube plus of z cube plus of 3y z squared. If I take this the derivative of y with respect to that of z. Okay. So first what I'm doing is basically finding out the gradient of phi with respect the gradient of phi at arbitrary point x, y, z. And then what I'm doing is basically I am putting the point P itself. Since I have to find out this gradient of phi at point P, and then I have to make a dot product with respect to that of in one cap. If I want to find out the directional derivative in this direction, in the direction in one cap, the directional derivative of one. So if I put the value of 2 minus 1 and 1, it comes to be 1 minus of 3j cap plus of 2k cap. I hope I am right. So this is coming to be 1. This is coming to be minus of 2, 1 minus of 3 plus of 8. So this is coming to be this is coming to be 2, 2 minus 1 plus 1 cube. So it is coming to be minus 3. Okay, it is right. And then this one is 3y z square. So if I actually put it to be like 3 minus 1 and 1 square, uh, this is coming to be 3 y is minus 1 and this is y square. So it is coming to be minus of 3. If we really comments 3y is minus 1 and so this 1 square minus of 3k. So this one is a vector you got, right? Pandira, I cap minus of 3j cap and minus of 3k cap, this one. So that dot product of I cap plus 2j cap plus 2k cap and this one divided by that of root over of 9. So this one will come as uh, 1 by 3, not minus 1 by 3. This is 1, this is 6. Sorry, this is 6. So this one is 3. So minus 11 by 3, which is minus of 3 2 by 3. This one should be cancelled. Minus 11 by 3. This one you got, right? Yeah, yeah. So, Lushik, that's the way it is basically working. Okay. So, did you got it? Yeah. So, now we are going to something which is called a tensor. So, I will give you a brief introduction about what is called a tensor. So, tensor tau is basically tau of ij, e I cap, e j cap. Okay. So, where I basically ranges from 1 to 3 and j basically ranges from 1 to 3, e tau ij, uh, e I cap, e j cap. So basically in the notation itself, for the sake of brevity, we basically don't write the sigma symbols here. So if I go to the tensor operation, similar to the one that we do in case of a vector operation, there is addition, subtraction, dot product between the two that I'm going to show you. So A tensor plus B tensor is basically equal to that of Aij, uh, Ei cap, Ej cap. So you always have a sigma symbol over there. So I can also write this minus, so we can combine the subtraction and addition at once. We can take it at once. So this is Aij, Bij, Ei cap, Ej. So these diodes should be same. So one thing I forgot to mention is that this product is called dyadic product. Ei cap, Ei cap, Ei cap, Ej cap. So these are basically called diodes. Okay, or dyadic product. So we are not doing any kind of dot product or scalar triple product. We are basically putting one unit vector beside another one. So the order of them are basically very much important. So Ei cap, Ej cap is basically not equal to Ej cap, Ei cap. Okay. But we are not doing any kind of dot product or scalar triple product or any kind of operation between the two. They are basically sitting beside each other, and the order of them in which it is written, it is important. Okay. So now T dot is this is basically a single dot product, what we call it to be, between two tensors. So this is basically Tij, Eij dot of Smn, En. So what I will do is basically I will make the dot product between the two unit vectors which are nearest to each other. So this will be equal to that of Tij Smn Ei En delta J. So T I J S J N E I E N. So J is basically equal to N. So that delta Jm is basically equal to 1. So whenever you get a canonical delta like this, so what you do is basically you make the indices to be same, that is J equal to M in this case, and then you put it in the equation so that you can get rid of the delta itself. Because any other combination where J is not equal to it, this will eventually give you a zero value of the canonical delta. Okay. So is it clear to all of you? Okay. So there is another thing which is called the double dot product. Let me do it. So double dot product is double dot E S M N E N or S I J. Let me A I J E I cap E J cap double dot E N N E N cap E N cap. Okay. So which is equal to S I J E N N, and then I'm going to do the dot product between the EI vector and the EN vector and EJ vector and EM vector. Since they are double dot, there will be two dot products. Okay, so this will be delta IN and this will be delta JN, the inner one. And then Sij is basically equal to TJI, since I equal to N and J equals to N. Is it clear to both of you? Okay. Then what? How do you define the transpose of a tensor? Okay. So A is tensor transpose S of Ij EI cap EJ cap transpose is basically equal to S of Ij EJ cap EI cap. So this is basically the transpose of a vector, tensor, sorry, transpose of a tensor. So what it does is basically it changes or it basically swaps the location of the two unit vector in a diagram. So EJ cap actually comes in the direction of EI cap and EI cap comes in the direction of EJ cap. That is basically called the transpose of a tensor. Okay. And then there is another thing which is called the dot product between a vector and a tensor. So vi cap dot enn en cap en cap. Okay. So this actually becomes what we should do is basically a dot product between the nearest unit vectors. So Vi, T, Mn, delta In, En cap. Okay. So Vi, T, In, En cap. So is it clear to all of you? Rushikesh Pandya? Okay. I think it is clear to both of you. And then there is another thing which is called the unit tensor. So I is basically equal to Ei cap, which is called the unit tensor. So if I want you to find out Ei cap dot dot Ej cap, or I want to find out this I dot gradient of it, double dot of the unit vector with the unit tensor with the gradient of it. Okay. So can you find it out, Pandya Raj and Rushikesh? So what you have to write is basically Ei cap, double dot, Ej cap, dvk, dxj, ek cap. Okay. So what you have to do is basically a dot product between Ej and Ej and Ei and Ek. Okay. So I hope you can find it out. So please simplify it. Pandya Raj and Rushikesh. This one should be I solved by the way. Ei cap, and double dot of Ej cap and this Ek cap itself. So are you able to understand it, Pandya Raj and Rushikesh? Okay, okay. Do it, do it. So I hope you can do it easily. Uh, so this actually reduces to a format which is EI and EI. So I can easily write it down as dvk dxj, delta of ij and delta of ik. So I equals to j equals to k. Okay. So which can be written as dvi dxa. So which is basically equal to divergence of v. Okay. Divergence of the vector v of vector. So is it clear to both of you? Okay. So this is a very preliminary lecture about the fluid dynamics part itself. So from tomorrow we will be going towards the line integral and the surface integral and the volume integral. And from there, by using that concept, we will use the concepts of CUT. So tomorrow I will be, not tomorrow, next week I will be discussing about the heat conduction problem, which I will do by using the finite difference or the finite volume method. By both method I will show you. So that thing we will do. And then after that, I will show you a simple coding of that, maybe in Octave, Python, or I think Octave is good. That's open source. So I will do that thing, and then we will. I will start giving you assignments, and then we can discuss that in the course. Okay. Okay. I think I can stop the recording.